So, revisions to your second paper are supposed to be done by Friday. Julio, that will obviously not include you. If you can get it, I still can get a chance to.
That's fine.
I'll get it to you right after class meeting. Okay, the fourth paper. So let's talk a little bit about what that is. Some of you got movies at the end of my last class. I have more. There are a total of about 8, 9 movies that have some good mathematical content that I was able to come across. So the two that are still in my package here are Agora, which is about Hypatia. And I just watched it recently. It's quite a good movie. And this movie, which came out just last spring, which is about Ramanujan, who's a really interesting story. He was a clerk in India and self-taught himself. Anyway, he became a self-taught mathematician. And he figured out stuff that other people, well, people are still looking through the notebooks of Ramanujan, taking these little gems that he just said, okay, here's a formula, it's true. He didn't even prove things, but he came up with stuff that was true. And people were like, yeah, it does seem to be true. We have no idea how it connects to the rest of the mathematical world. Ramanujan is an interesting tale. He ended up writing a letter to G.H. Harding, who's the guy with the hat on the hair, is an English mathematician. Got invited to come to Cambridge. He got sick while he was there and then died.
Can I have that movie?
Ramanujan? No, it's Hypatia.
Is that?
Let's take Hypatia. So everybody, not everybody has a movie yet, right? So the next thing I want to ask is, please try to view the movies quickly so we can redistribute. Who hasn't got a movie at this point? 1, 2, 3, 4, 5, 6. Oh, okay, great. Yeah, if you've got another source for it, like Netflix or Amazon Prime or something. Anybody want to do 21? This is modern, not really history, but there's math content.
It's got Kevin Spacey in it.
It is about blackjack.
It's got Kevin Spacey in it.
I will, yeah, I'm going to do that. So, yeah, that way you can find out what they are, and maybe you can find them from other sources. I imagine you're going to want to watch your movie at least twice, so get an initial watch on it, and then try to give it to somebody else, but then be able to get it back from them for your second watch. They're quite nice together. We could even do like a movie night if you want, like together on Saturday. That's perfect. Now that's just like big monitor, what do they call TV. It has a big TV in the lounge area, so yeah. So what's the point of this paper? It should be a movie review, that's true. But these are movies that all have mathematical content. So I really want you to comment on the maths more than the storyline. It certainly includes some stuff about the story to kind of focus what the stuff is talking about. But you don't have to rely just on your own opinions about this stuff. Google, find Wikipedia entries, or even IMDb may have. Everybody know IMDb? So that may have some sources about whether the math content is good or lacks. But that's the idea, to mostly comment on the mathematics that's told in the movie. Sometimes they did a really good job with portraying the mathematical content. Other times not so much. Like, Who Got a Beautiful Mind? Great movie. The mathematician they studied, John Nash, is an amazing genius, but they were really more interested in the aspect that he went crazy. He sort of lost his mind, and eventually came back. The way they treat his math is really weak, so we should talk.
Do you want like a 1 or 2 paragraph synopsis of the movie and then like all math content?
Well, I wouldn't maybe go that far. You're going to need to write up 3 pages. So maybe the first page would be synopsis and general feelings about the movie that you liked it, what didn't stink. Okay. But then spend the bulk of the paper talking about 2 out of 3 pages. I don't want to be too specific on that. Okay. So then the last thing on our startup page, we need to have a midterm. Yeah. So the question, I was originally going to say, okay, Friday, and then I saw it was the 13th, and I was like, no, nobody wants Friday the 13th.
Lucky day, I would love
That's
to.
fine.
You're fine with Friday the 13th?
Friday.
Yeah.
Okay, let's go with Friday the 13th.
That sounds ominous. I'm sorry.
Crazy. So,
Before we go on, two quick questions on the paper.
yes,
What is it?
it will be due in approximately 4 weeks.
4 weeks. Oh,
So you need about 1 week to get the movie under your belt. You may want to watch it a third time even later in there. I will give you a serious due date on that. Approximately.
and how do you want it? LaTeX again? Or?
Yeah, let's do 10. One thing I wanted to ask about the third paper, how do people feel about copying and pasting that into a wiki entry too? So we can, I think it would be fun for the course just to be able to build out the wiki and then we can look at one another's bios.
Can you go on LaTeX and show me how to do the line spacing?
Yeah, let me just put this calendar entry here. The command to get line spacing, double spaced.
Yeah, I didn't know where to put it, and I kept getting an error.
So the very first line in your document should say document class. And then you can give options. I usually ask people to put in 12-point as an option. That way it's easier to read. But the main thing is what kind of document it is. We use the article document class most of the time. But there's other things that you do there. You have books, you have reports, things like that. So from there to way down below that, actually a long ways below that, you'll find the thing that actually starts the document. This is the end document. So all the stuff in between where it says document class on the first line and where you finally actually begin writing right after this is called the header. Everything in here is header. So you can put this anywhere in there. It doesn't matter exactly where, as long as it happens before the slash begin document.
Okay.
Put in slash, line spread. All the tech or LaTeX commands begin with a backslash. Two. That'll get you double squiggle. Did I say this right too? Those of you who've done it. Yeah, give that a try. See how it works. So I had these guys in last class observing a class, and I got, at some point I hit this YouTube video that I wanted to show you, and I just went in I had to show them like 6 YouTube videos in a row. These guys are gonna like call me out on that, so I skipped this one, but I want us to see this. I think it's an interesting text, and this is a cool thing.
The great texts of the ancient world don't survive to us in their original form. They survive because medieval scribes copied them and copied them and copied them. And so it is with Archimedes, the great Greek mathematician. Everything we know about Archimedes as a mathematician, we know about because of just 3 books, and they're called A, B, and C. And A was lost by an Italian humanist in 1564, and B was last heard of in the Pope's library about 100 miles north of Rome in Viterbo in 1311. Now Codex C was only discovered in 1906, and it landed on my desk in Baltimore on the 19th of January 1999. And this is Codex C here. Now, Codex C is actually buried in this book. It's buried treasure, because this book is actually a prayer book. It was finished by a guy called Johannes Myronas on the 14th of April, 1229. And to make his prayer book, he used parchment. But he didn't use new parchment, he used parchment recycled from earlier manuscripts, and there were 7 of them. And Archimedes' Codex C was just one of those 7. He took apart the Archimedes manuscript and the other 7 manuscripts. He erased all of their texts, and then he cut the sheets down in the middle, he shuffled them up, and he rotated them 90 degrees, and he wrote prayers on top of these books. And essentially, these 7 manuscripts disappeared for 700 years, and we have a prayer book. The prayer book was discovered by this guy, Johann Ludwig Heiberg, in 1906, and with just a magnifying glass, he transcribed as much of the text as he could. And the thing is that he found 2 texts in this manuscript that were unique texts. They weren't in A and B at all. They were completely new texts by Archimedes, and they were called the Method and the Stomachion. And it became a world-famous manuscript. Now, it should be clear by now that this book is in bad condition. It got in worse condition in the 20th century, after Heiberg saw it. Forgeries were painted over it, and it suffered very badly from mold. This book is the definition of a write-off. It's the sort of book that you thought would be in an institution. But it's not in an institution. It was bought by a private owner in 1998. Why did he buy this book? Because he wanted to make that which was fragile safe. He wanted to make that which was unique ubiquitous. He wanted to make that which was expensive free. And he wanted to do this as a matter of principle, because not many people are really going to read Archimedes in ancient Greek, but they should have the chance to do it. So he gathered around himself the friends of Archimedes, and he promised to pay for all the work. And it was an expensive job, but actually it wouldn't be as much as you think, because these people, they didn't come for money. They came from Archimedes, and they came from all sorts of different backgrounds. They came from particle physics, they came from classical philology, they came from book conservation, they came from ancient mathematics, they came from data management, they came from scientific imaging and program management, and they got together to work on this manuscript. The first problem was a conservation problem, and this is the sort of thing we had to deal with. There was glue on the spine of the book, and if you look at this photograph carefully, in the bottom half of this is rather brown, and that glue is hide glue. Now, if you're a conservator, you can take off this glue reasonably easily. The top half is Elmer's wood glue. It's polyvinyl acetate emulsion that doesn't dissolve in water once it's dry, and it's much tougher than the parchment that it was written on. And so before we could start imaging Archimedes, we had to take this book apart. So it took 4 years to take apart, and this is a rare action shot, ladies and gentlemen. Another thing is that we had to get rid of all the wax, because this was used in the liturgical services of the Greek Orthodox Church, and they used candle wax, and the candle wax was dirty, and we couldn't image through the wax. So very carefully we had to mechanically scrape off all the wax. It's hard to tell you exactly how bad this condition of this book is, but it came out in little bits very often. And normally in a book you wouldn't worry about the little bits, but these little bits might contain unique Archimedes text. So tiny fragments we actually managed to put back in the right place. Then, having done that, we started to image the manuscript, and we imaged the manuscript in 14 different wavebands of light. Because if you look at something in different wavebands of light, you see different things. And here is an image of a page imaged in 14 different wavebands of light. But none of them worked. So what we did was we processed the images together. We put 2 images into one blank screen, and here are 2 different images of the Archimedes manuscript. And the image on the left is a normal red image, and the image on the right is an ultraviolet image. And in the image on the right, you might be able to see some of the Archimedes writing. If you merge them together into one digital canvas, the parchment is bright in both images, and it comes out bright. The prayer book is dark in both images, and it comes out dark. The Archimedes text is dark in one image and bright in another, and it'll come out dark but red, and then you can start to read it rather clearly. And that's what it looks like. Now, that's a before and after image, but you don't read the image on the screen like that. You zoom in, and you zoom in, and you zoom in, and you zoom in, and you can just read it now. process the same two images in a different way, you can actually get rid of the prayer book text. And this is terribly important because the diagrams in the manuscript are the unique source for the diagrams that Archimedes drew in the sand in the 4th century BC. And there they are, I can give them to you. With this kind of imaging, this kind of infrared, ultraviolet, and visible light imaging, we were never going to image through the gold ground forgeries. How were we going to do that? Well, we took the manuscript and we decided to image it in X-ray fluorescence imaging. So an X-ray comes in the diagram on the left, and it knocks out an electron from the inner shell of an atom. And that electron disappears. And as it disappears, an electron from a shell further out jumps in and takes its place. And when it takes its place, it sheds electromagnetic radiation. It sheds an X-ray. And this X-ray is specific in its wavelength to the atom that it hits. And what we wanted to get was the iron, because the ink was written in iron. And if we can map where this X-ray that comes out, where it comes from, we can map all the iron on the page, and theoretically, we can read the image. The thing is that you need a very powerful light source to do this, so we took it to the Stanford Synchrotron Radiation Laboratory in California, which is a particle accelerator. Electrons go around one way, positrons go around the other, they meet in the middle, and they create subatomic particles like the charm quark and the tau lepton. Now, we weren't actually going to put Archimedes in that beam, but as the electrons go round at the speed of light, they shed X-rays, and this is the most powerful light source in the solar system. This is called synchrotron radiation, and it's normally used to look at things like proteins and that sort of thing, but we wanted to look at atoms, at iron atoms, so that we could read the page from before and after. And lo and behold, we found that we could do it. It took about 17 minutes to do a single page. So, what did we discover? Well, one of the unique texts in Archimedes is called the Stomachion, and this didn't exist in codices A and B. And we knew that it involved this square, and this is a perfect square, and it's divided into 14 bits. But no one knew what Archimedes was doing with these 14 bits, and now we think we know. He was trying to work out how many ways you can recombine those 14 bits and still make a perfect square. Anyone want to guess the answer? Okay, it's 17,152 divided into 536 families. And the important point about this is that it's the earliest study in combinatorics in mathematics. And combinatorics is a wonderful and interesting branch of mathematics. The really astonishing thing, though, about this manuscript is that we looked at the other manuscripts that the palimpsester had made, the scribe had made, his book out of, and one of them was a manuscript containing text by Hyperides. Now, Hyperides was an Athenian orator from the 3rd, 4th century BC. He was an exact contemporary of Demosthenes. And in 338 BC, he and Demosthenes together decided that they wanted to stand up to the military might of Philip of Macedon. So Athens and Thebes went out to fight Philip of Macedon. This was a bad idea because Philip of Macedon had a son called Alexander the Great, and they lost the Battle of Chaeronea. Alexander the Great went on to conquer the known world. Hyperides found himself on trial for treason. And this is the speech that he gave when he was on trial. And it's a great speech. Best of all, he says, is to win. But if you can't win, then you should fight for a noble cause, because then you'll be remembered. Consider the Spartans. They've won innumerable victories, but no one remembers what they are, because they were all fought for selfish ends. The one battle that the Spartans fought that everybody remembers is the Battle of Thermopylae, where they were butchered to a man who fought for the freedom of Greece. It was such a great speech that the Athenian law courts let him off. He lived for another 10 years. Then the Macedonian faction caught up with him. They cut out his tongue in mockery of his oratory, and no one knows what they did with his body. So this is the discovery of a lost voice from antiquity, speaking to us, not from the grave, because his grave doesn't exist, but from the Athenian law courts. Now, I should say at this point that normally when you're looking at medieval manuscripts that have been scraped off, you don't find unique texts, and to find 2 in one manuscript is really something. To find 3 is completely weird, and we found 3. Aristotle's Categories is one of the foundational texts of Western philosophy, and we found a 3rd century AD commentary on it, possibly by Galen and probably by Porphyry. Now, all this data that we collected, all the images, all the raw images, all the transcriptions that we made and that sort of thing, have been put online under a Creative Commons license for anyone to use for any commercial purpose. Why did the owner of the manuscript do this? He did this because he understands data as well as books. Now, the thing to do with books, if you want to ensure their long-term utility, is to hide them away in closets and let very few people look at them. The thing to do with data, if you want it to survive, is to let it out and have everybody have it with as little control on that data as possible. And that's what he did. And institutions can learn from this, because institutions at the moment confine their data with copyright restrictions and that sort of thing. And if you want to look at medieval manuscripts on the web, at the moment you have to go to the National Library of Y's site or the University Library of X's site, which is about the most boring way in which you can deal with digital data. What you want to do is to aggregate it all together. Because the web of ancient manuscripts of the future isn't going to be built by institutions. It's going to be built by users, by people who get this data together, by people who want to aggregate all sorts of maps from wherever they come from, all sorts of medieval romances from wherever they come from. People who just want to curate their own glorious selection of beautiful things, and that is the future of the web, and it's an attractive and beautiful future if only we can make it happen. Now, we at the Walters Art Museum have followed this example, and we have put up all our manuscripts on the web for people to enjoy, all the raw data, all the descriptions, all the metadata, under a Creative Commons license. Now, the Walters Art Museum is a small museum and has beautiful manuscripts, but the data is fantastic. And the result of this is that if you do a Google search on images right now and you type in illuminated manuscript Quran, for example, 24 of the 28 images you'll find come from my institution. Now, let's think about this for a minute. What's in it for the institution? There are all sorts of things that are in it for the institution. You can talk about the humanities and that sort of thing, but let's talk about selfish things. Because what's really in it for the institution is this. Now, why do people go to the Louvre? They're called A, B, and C. And A...
More so than the codex itself. So. And I'm actually a big proponent of open source, so I feel kind of weird cutting him off about that. But I did want to point out one error in the speech that he just made. He said this was available for free use for any commercial use. And he meant to say non-commercial. Right. It's actually licensed under so you can't try to make money off the Archimedes Codex, but you can. I suppose you can. You can't say that you got it from the Walters Art Gallery. It might be interesting to see if you can make money from Archimedes. Okay, so let me get back to our next thing. The next pair of mathematicians we're going to look at are David Mathis, who's this is CE, not BCE anymore. We're finally passed into the current numbering system for years. But you see all the question marks on that? Diophantus is known as the father of algebra, but we have very little idea when he even lived, right? And part of any information about him, like, nobody knows who his parents were. There's usually some historical detail about these characters. Nothing. So the guess is that he was born around 200, and that has in writing his works in 230 to 250. And that's a guess because some of the stuff in there he quotes other people, and we knew when they had written, so it has to be after X. And then other people later on made commentaries on him, so we know he wrote it before them. Right? So it's sort of a narrowing down. But this is really a broad guess. It could be almost 100 years in either direction. On the other hand, the span of his life is believed to be correct there, that it's 84 years. And it's because there's this famous problem that was posed in a book called Greek Anthology. Came out around 500 AD, so I said AD there instead of CE. It's okay. Anyway, that's, what, 300 years after, or at least 200 years after his death. But they have this puzzle about the Diophantus, and it's a remarkable puzzle. So they're talking about Francis. It says his boy act put lasted 1/6 of his life. He married after 1/7 more. His beard grew after 1/12 more, and his son was born 5 years later. The son lived to half his father's age, and the father died 4 years after the son. Can you take that information and figure out how old he was when he died? Yeah, me either. But they're claiming it's 84 years, so it might be worth trying to check this based on the fact that the answer supposedly is 84. The method that you use to solve that type of problem, and there is a method, is something called studying number theory. The last time we offered number theory, 5 people signed up for it, so it did not run. But I would encourage you, if you see number theory on the list, this is a great elective course for math people. And even, physics majors or something like that. So, but let's check that 84 actually works. If his total lifespan was 84, how long is this boyhood part? That's 1/6 of his life. How much?
16.
14?
84 into 14?
Yeah.
I gotta do that the other way. 6 times 14 is 16, 24. So we got 14 years for the boyhood. And then 1/7 of 84? Can you do that one?
16?
16?
Was he married at 16?
No, but 7 times 16 is too big.
Right. It was
Is
1/7.
it 12? Yeah, if you know heights in inches, 84 inches is a funny number. It's 7 feet tall. If you're 6 feet tall, you're 72 inches. 1 foot on the top of that is 84. So 7 feet, that is 12. So after his boyhood ended at 14, he waited 12 more years. So he's 26 when he got married. Now, I don't know about this. His beard grew at 12 more.
I feel like that's irrelevant.
You think what?
That's like irrelevant. You don't even need to know about his beard.
Well, you don't, but you see, it's at the end of that 1/12 more that we get his son born 5 years later. Right? So what is 1/12 of 7 feet? 7. Yeah. Then the son is born 5 years later. And then if these two things are right, the son lived to half his father's age, how long did the son live? Assuming he really lived 84 years, 42. And then the father dies 4 years after that. So, does this all add up to 84?
Yeah.
Now, but the method that you use to actually, we're checking the answer, right? But the method you use to solve a problem like this is hard and interesting. It's named after New Francis. So yeah, father of algebra, not so much. What he did was begin the process that moves us towards what we consider algebra. For instance, he didn't use X. He didn't have the things for variables. He had special symbols for the unknown, but it wasn't like letters for unknown quantities. So he got something that starts to approach formalism that we use for algebra. He had symbols for the unknown and for its powers. That's good. Of course, he had the numbers. He had, I think they say it was an abbreviation. I imagine he had the Greek phrase for this is equal to that and turned it into a little acronym or something. Not something as simple as this on it. Still, here's some of the downsides. If he had more than one variable, the symbols had to be reused, and he had to talk about, okay, this is the expression for the first unknown, and here's the expression. He had to put words in to distinguish X from Y. Yeah, it's a little bit of a shortcoming, which is why eventually we decided to start using letters for this stuff. He considered that if you got anything other than a positive fractional answer, something had gone wrong. He just said, those are absurd. How can you have -3 books? But we all believe in negatives, don't we? You can have money in the bank, or you can owe money. So you can have negative quantities. That's reasonable. And irrational numbers, I don't think they bother us today at all. They just get some decimals, get as many decimal places as you need to describe a number. Who cares that it's not a fraction? Let me point out how he had to deal with the quadratic formula, or not, sorry, I should say quadratic equations, because of this prejudice against negatives. If we have something like x squared minus 3x plus 12, that's all we write. But he would have liked this negative thing, so he would have turned this into x squared plus 12 is equal to 3x. I'm sorry, I should have said equal to 0 on that. So he would twist things around until none of the coefficients were negative. You should see that there's not that many possibilities for what you have to do if you've got some negative numbers in the coefficients. You get things that look like x squared, ax squared equals bx plus c, which is what would happen if both b and c were negative. You'll have ax squared plus bx equals c, which is the kind of thing you get if c is the only one that's negative but the other two are positive. And then what else is there? Ax squared plus c dx. What you get if b was negative. If all three of the terms were negative, he'd realize you could negate the whole thing and you could still write it as positive. So you didn't have to deal with this separate case of that. And I guess as well as these three, there would have been the more general one that we consider today is the whole deal. If all three numbers are positive, you just have that. So it added a lot of complication, right? He probably had to deal with 3 different cases for quadratic formulas. Now, I wonder if people have heard about the story of Fermat. Yeah.
Augustin Fermat?
Pierre de Fermat
Yeah, Fermat.
was a French mathematician in the late 1600s, and after he died, they found a book that he had been working on, where in the book was looking at the Pythagorean relation, x squared plus y squared equals z squared, and talking about Pythagorean triples, finding out a whole number of solutions to that. And in the margin of the book, which was a fairly big thing, so the rest of the text is here. Margins, the guy had written, but x to the n plus y to the n equals z to the n has no solutions, except trivial ones. Provided n is bigger than 2. You see that you could get trivial solutions. What do they mean by a trivial solution? Well, like if x and y and z were all 0, that works. If x was 1, y was 0, then z would 1 would work. Even if the power was greater than 2, you could get certain solutions. But those are kind of the lame ones. We want to think like 3, 4, 5 working in that formula. Not a whole bunch of zeros. Okay, so Fermat had written this in the margin, and then he said these famous words, I have a miraculous argument for why this is so, but the margin is too small. So for 400 years, people were wondering, what was it? Fermat was good. He was a well-known and respected mathematician, although he was an amateur. He didn't work as a professional mathematician. He was actually a lawyer, but he had done a lot of work, and people knew him, and they believed that he had a proof. And for 400 years, people have been trying to find a proof. In the 1990s, somebody finally proved this statement. But the argument they used was totally modern. There was no way Fermat had any idea. It was about elliptic curves and modular proofs and things. So anyway, his writing that he had this miraculous proof that the margin is too small was referring to this book, The Arithmetica by Diophantus. He had a copy of it. There was a translation, actually, but so it was sort of a copy. The Arithmetica is really quite famous, and it had 13 books in it. About half of them must have disappeared almost immediately. They just got lost. Diophantus was in Alexandria, so I don't know why they didn't end up in the library. We're going to talk about Hypatia probably on Friday now, but she wrote a commentary, and it ends on book 6. So they kind of think that the rest of the stuff was not available to her. So somehow they dropped a lot of the right away. What's mostly in these books, these first 6 anyway, I don't know about the other thing, are the problems, the solutions of methods for these kinds of problems we just looked at, the age thing. Not checking it, but actually finding the answer. And those are called Diophantian problems. There's evidence that he knew some very modern results. And I'll just give you one example. Well, there's probably 2 examples I should mention. One of them is that if you have the difference of 2 cubes, you can always find 2 other numbers so that that's the sum of their cubes. This is for rational numbers. So if anytime you have 2 rational numbers and you cube them and take the difference, whatever that number is, it's possible to find 2 other rational numbers and sum them, and sum their cubes and get that number. That's a strange, and that's a Diophantian equation. He didn't prove that, but he appears to have used that fact, used it as a tool. The one that's in the text, or that's in my slide rather, is a brilliant thing called the 4-square theorem. And this was known by Euler in like 1600s, but it didn't get proved until Lagrange did it in 1770. I have seen Lagrange's original proof of this. It's in French. It could have been in Latin at that time, but he did it in French. And it's pretty readable, but it's 3 or 4 pages long. Right? This is not, if you're in the Math 250, do your proofs end up to be 4 pages long? If they are, you're probably messing up. But this was as concise as you could make it, and it's still 4 pages long. This is an intricate argument. What it says, though, is probably what we want to talk about first. It says that if you have any number whatsoever, you can always write it as a sum of squares. But you never need more than 4. 4 is the max. So you should try this on a few numbers. Can you figure out how to write various numbers as the sums of squares? And do it efficiently, so you don't need too many squares. I guess I could get started with silly examples. 1 is, of course, 1 squared, so I only need a single square for that. And 2 is 1 squared plus 1 squared. 3, 1 squared. How about if I just keep going like that, just adding 1 squared over and over again? Well, I don't want to do that. When I get to 4, I can just say it's 2 squared. How about writing 5 as a sum of squares?
2 squares plus 1 square.
4 squared, 2 squared plus 1 squared. Okay. This was too easy. Huh? We haven't needed 4 yet, have we? What would you expect to need 4 for the first time? I could definitely do 6 with 2 squared plus 1 squared plus 1 squared. 7, is it going to have to be 3 ones? 7 is the first one that actually requires 4 numbers, 4 squares. Because 8, you get to bump down and do it as 2 squared plus 2 squared. Let me, what about 15? Can you do that one?
3 squared plus
3 squared is 9, and now we got 6 more to get in there.
Plus 2 squared.
I skipped 6. Should I throw a 2 squared in there?
yes,
3 squared. So 9 and 4, that's 13.
Plus 1
plus 1 square plus 1 square.
14 and 15? Yeah, a couple of 1 squares will do it. So we're finding that it seems to be possible that we don't ever need to use more than 4 squares. Lagrange proved it. Diophantus apparently knew it. Okay. Yeah, I think I'll close out early because I had decided last night at midnight that I was going to wait on vacation for Friday. And I think that's just as well because we just decided to move the exam to Friday this week. So that date is wrong on there. I said 10/11, but it'll now be 10/13. That's going to be popular. Take a look at those videos as soon as you can so that we can distribute them to other people who want to use them. And I will put up a list of the videos so that try to look for other sources of them.